The key to high throughput assembly is to parallelize the processes, to speed up these processes, and to avoid any unnecessary movement. Sooner or later, this leads to continuous material flow, and we are especially interested in such elaborated assembly processes which happen while in motion. To assemble objects while they travel at high velocity is a challenge by itself. Just like astronauts have to face the problem when they dock their spacecraft at the International Space Station. This challenge of on-the-fly assembly becomes even harder when the number of objects to be placed accurately increases beyond 2. Our particular problem is located in the field of battery production. In the kind of process you're looking at, electrodes need to be placed on top of a web, and that web must be folded just like I show you here. So the challenge there is to do it at a very high throughput while maintaining the accuracy of the adjacent electrodes which come to lie next to each other. So, welcome to my presentation. It's a pleasure that you take the time to come to this presentation, to attend the presentation. I'm really looking forward to your comment and questions. Welcome. To introduce, let me give you some project context at first. I will then structure the problem and present the method that we have used in our particular problem. I will report about a showcase where we have applied the methods, and we will see some practicalities that we have learned during this application. Inside a lithium-ion battery, the deviation of the electrodes with respect to the target assembly position is a crucial factor, a crucial property of this battery in terms of functionality and safety. In industry, the target is not to bring this down to 0, but it is to bring it to an acceptable level and then improve and maximize the productivity for this kind of acceptable misplacement. Also at TU Berlin, we are concerned with high throughput assembly of this electrode separator compound. And the first project that we have done in this purpose was the project ProTruck, where the purpose was to develop high-speed electrode sheet depalletizing and feeding with an in-situ deviation correction. This feeding technology was included in the project Contibat that we are working on right now, where the target is to demonstrate a continuous web-based Z-folding of battery stacks. So the idea of this is to take the feeding input of the previous project and then to develop a folding mechanism that would create the electrode separator component in a continuous manner. Together with TU Braunschweig and with the Fraunhofer Institute, we have started a project where we aim even higher for productivity. In this project, also a totally new process concept is being investigated, which will be by principle be superior over common known principles. At the core of this project is to simulate these high-speed handling and assembly process in detail in order to predict the details of these processes. Our contribution from Berlin to this project is mainly the feeding mechanism with very high throughput and very high accuracy so that the downstream process can be fed with very low uncertainty. For example, you can see here a high-speed lift-off simulation that we have made in that project so far. In all these projects about high-throughput assembly of battery compounds, we've learned that a productivity increase mostly means that also a more complex process kinematics is needed. This means also that accuracy-relevant effects become more complex, and we also have found that accuracy-relevant methods are not elaborate enough to control these more complex problems. The following section revolves around the types of assembly processes that can be found when a web-driven process is under investigation. The first type of web-based assembly that I'd like to denote is where a workpiece is assembled onto a web. In this kind of assembly process, each of these workpieces has their distinctive target location, and the main target is to place the workpiece as close as possible on top of this target location. In a roll-to-roll type of process, two base materials are joined together and then are wound again onto a roll. The accuracy is defined in a lateral way and in a longitudinal way. And as long as the base materials are rigid, there is one relative movement of the two base materials, and all the target assembly locations are affected in the same way by this. The type 3 I wanted to show is the so-called roll-to-stack winding. This is a process where battery electrodes are placed on a separator, and then the separator is wound to a stack at the end of the process. The fourth type I'd like to introduce is roll-to-stack folding. This means that the base material comes from a roll, then discrete elements are placed on top of that, and then a fold is created, where not only the accuracy of the placement is important, but it's also the placement of the folds that determine the final accuracy in the product. The further elaborations in this presentation will concentrate on this type 4 because we found that all the aspects that can be found in the previous types are aggregated in this type 4. The accuracy relevant effects I'd like to talk about are classified with respect to two different aspects. The first is whether these effects are systematic errors or stochastic errors. The second way to categorize is whether these effects are static effects, which means that as the time tends towards infinity, or whether these are dynamic effects that can be observed. So we see, for example, effects of an imperfect kinematic model, imperfect adjustments in the machine, imperfectness or tracking errors from the control law, forces from elasticity in the web material. We also see errors that arise from poor machine design and components. We also see static errors that come from gripping and joining processes, as well as disturbance forces that are created or transmitted by the machine and the components, or by straying material properties. And we see vibrations that might have an effect that degrades the accuracy. This all sums up so that in the end, the assembly misplacement is obtained. Questions that arise are now, and how does an error input affect the final assembly? What should be emphasized in phase of the machine design, and how can, in a concrete assembly situation, how can a suitable compensation input be determined? In our work, we were mainly interested at first to find a method that helps us find ways to build the machine the first time right. So we needed a method that supported us during the phase of the concept and of the detailed design of the machine components we had to develop for ourselves. In our research for existing methods, we found methods for robots and manufacturing machines, which are mainly concerned in single-end effectors. We found a precision assembly of discrete workpieces, and also there the main occupation is to align two reference frames per assembly next to each other. And we found a roll-to-roll assembly where mostly lateral alignment is sought after, and not the longitudinal that we are looking at. So the objective is to find a kinematic modeling which considers more than two reference frames to be aligned for accuracy analysis and for calibration purposes. Moreover, we'd like to quantify the contribution of the tunable parameters in the machine to the overall assembly accuracy. Ultimately, we were looking for guidance on how to improve the accuracy by improvements in the machine. Now I'd like to present the method that we've elaborated and used for our project. We propose to use 5 stages. In the first stage, the definition of accuracy variables and reference points takes place. So the second stage is about kinematic decomposition and modeling. In the third stage, deviation description and sensitivity analysis takes place. The fourth stage is an experimental one where it is about measurement and estimation of the input accuracy. And in stage 5, the final stage is about output accuracy analysis and system improvement. At first, locations are defined where the assembly accuracy is of interest. In our practical case, this is the alignment or the misplacement of 2 adjacent electrodes. Subsequently, points of particular interest on the web are defined as so-called dynamic reference points. These could be, for example, gripper points or points where folds are to be placed or other points that are of interest. In the kinematic modeling later, these will be the outputs of the interim kinematic model. These points are denoted in the assembly kinematics so that they can be found not only on the product but also in the machine. In stage 2, the kinematic decomposition and modeling takes place. The kinematic decomposition can be seen on the sketch on the right-hand side, where the kinematic system is decomposed in multiple stages. This is to simplify the kinematic model in each of the sections and then to couple them by dynamic reference points. Then the kinematic model is developed for each of these sections so that the dynamic reference points are outputs of this model and the inputs are the actuator locations and the tunable parameters here denoted as theta. The second equation, XACC, denotes the position of the accuracy variables that have been defined initially, and it is built on top of the dynamic reference points. In stage 3, the deviation is described and the sensitivity is analyzed. This is done by the differential of the kinematic model. So both of the kinematic model are differentiated so that each of the influences, say the actuator locations and the tunable parameters, can be used to project on the end effector, also the dynamic reference points, and also towards the accuracy variables. The final output of this is the misplacement of the assembly target location with respect to a deviation at one of the inputs. Stage 4 seeks for data about the input uncertainty. Mainly the covariance of each of the inputs is sought. This is either done by experiment or by a priori knowledge, let's say by data sheets or other information that is available beforehand. There are now 2 methods to project these input uncertainties onto the targeted assembly accuracy. The first is to multiply the covariances individually and then sum them up on the accuracy variable. The second strategy is to use a Monte Carlo simulation of stochastically distributed input combinations and then to model the output deviation distribution. In stage 5, one looks after parameters where the assembly covariance is very high and or where the sensitivity is very high. So in order to improve, 2 basic strategies can be used. The first one is to reduce the input covariance by either more precise machine components and or more precise handling and joining processes. The second improvement that can be sought after is to reduce the sensitivity by redesign of the mechanism. We are totally aware that this method implies simplifications and assumptions, so that it is not really straightforward to do a prediction of the absolute assembly accuracy. However, this method is very useful to find a ranking of accuracy influences. So if one looks for the most beneficial methods to improve the accuracy, then the ranking of the different projected input uncertainties is a good idea to start with. I would now like to share some insights that we have found in our project, and I'd like to put that one in a case study where we have gone through all the stages that I have presented before. So we started with the idealized electrode separator package, where we defined the accuracy variables, as I said before, along the adjacent electrodes, and we defined that we needed dynamic reference points at the locations where the grippers would grip the separator material and then do the folding. In order to explain the decomposition and the modeling, I'd like to share a more detailed view on the process kinematics. The process kinematics were decomposed into three sections. The first section is the assembly of the web with the discrete electrodes. There is a joining process. In section 2, there is the connection between the gripper and the fold is created. Section 3 is then where the guidance of the fold along the folding path takes place. Here you can see an illustration of the folding kinematics in section 3. It looks very straight in this animation, but consider that as the fold approaches its final destination, there are some curved segments in there which are very small deviations, but which are very, very significant for the web tension, as we have found in our practical experiments. Stage 2 was occupied with the kinematic modeling also. I'd like to show you a little excerpt of this kinematic modeling as a representative for the other sections as well. You can see here section 2 being modeled. You see that 6 drive locations are indicated, and you can see 3 dynamic reference points. The motion in total is an endless motion. However, it repeats after 2 folds. Since the machine and the process is symmetrical, these 2 folds are identical in a mirrored way. We went through stage 3, where the assembly misplacement is derived from the actuator deviations and the deviations of tunable parameters, and then there is looked at the deviation at the electrode misplacement in the assembly. The numerical results of this sensitivity analysis have shown that the actuator number 3, which you can find in the lower left of the sketch, the actuator number 3 has the highest sensitivity. So in the following, this will be the drive, or the actuator with the most priority for improvement. According to the ranking of the sensitivity and the output uncertainty contribution, we have made a ranking of priority, how much effort we wanted to put into the input uncertainty data. For example, actuators Q3 and Q5, we decided to use extended experiments for them because of the very high sensitivity of the final output. Actuators Q1 and Q2, we've taken that data from datasheet, and actuators Q4 and Q6, we have postponed that because we found that the sensitivity is way lower than the others. So after this data, we predicted that the machine would add an uncertainty by 0.1 millimeter at the assembly output. This was based on a Monte Carlo simulation that we've made on the basis that at the intake, the misplacement would have 0.2 millimeters and the expected assembly misplacement at the stack assembly would be 0.3 millimeters. We are fully aware that there is a number of assumptions and simplifications of that, and we are not so much interested in the absolute numbers at the moment, but we're interested in guidance for improvements here right now in the current project stage. I'd like to show you two examples of such improvements. The first one I'd like to show you is the redesign of the gripper and mover, where we have strengthened our emphasis on the accuracy in the actuators Q3 and Q5. On the right hand side, you can see an augmented reality animation of the whole machine and the process. So the machine will fold away so that the process will become visible. I'd like to direct your attention to these moving parts on that red panes where the gripper and mover systems are rolling around, cycling around this mechanism. So after finding out that Q3 and Q5 are of most importance, we did a redesign of that. So we improved stiffness in various directions there. We made extra effort to calibrate gripper edge locations and to put them for each individual gripper, to put that into the control software. We were also considering that a compliant mechanism or even an active actuator would be helpful in the directions 4 and 6. And also we found out that vibrations would be really significant, vibrations that occur on the basis of the really high accelerations that the system achieves. So that we redesigned these movers such that the center of mass is adjusted and the buildup of vibration is minimized. The second improvement I'd like to show you is about the adjustments in the tunable kinematic parameters that we refined. The first thing that was improved was that an emphasis was put on the high repeatability of the gripping point, which led us to an increase of track length in the machine. Also, we put more emphasis on very low deviations in the static placement point. We integrated an adjustability for the alignment of the track system. We used also a process integrated calibration for each individual actuator in the system. In order to suppress vibrations, we made extra effort to optimize the control parameters in each segment of this curved trajectory that the movers do. We did the experimentation and tuned in practice the parameters so that the vibrations would remain at a minimum. There is a number of more improvements that we will not be able to show you here in this presentation. You're really invited to get the PhD thesis of Arne Glodde. It is already available from our website, so feel free to take a look into that. Get in touch with us, get in touch and discuss with us. We're really happy to create some interaction with you. Let me summarize. We came from the problem of continuous stacking of separators and electrodes, which needs to be very accurate to yield a good quality battery. Currently, we're working on a kind of high throughput process for this purpose, which folds a web in continuous motion. While the throughput is improved by such concepts, this involves complex kinematics and complex accuracy effects. It is particularly the increased number of interconnected variables and effects that make the accuracy so hard to control. Our paper addresses this need for accuracy control and extends existing methods for kinematic accuracy analysis. Now there's a method for assembly situations where more than two elements need to be joined to each other. We've learned that the first main challenge lies in the nomenclature and the complexity of the kinematic model. To check the model and its implementations for correctness is a task with practical pitfalls one should not underestimate. The second main challenge lies in the experimental measurements needed. We could not find measurement technologies sophisticated enough for all variables we sought, so that we needed to improvise or use a priori knowledge to guess. I'm sure future innovations will address this issue. In the future of our work, it is planned to integrate sensor guidance into the assembly process. This shall compensate most of the uncertainty at the machine intake, and I am looking forward very much to see this advancement in action. The work we have reported in this presentation would not be feasible without the hard work of the whole project team. Let me express my appreciation to my co-authors, Arne Glodde and Cesar Solmas, but also beyond to the whole project team, namely Robert Moye, Muhammad Aldemir and Alexander Müller. It is your contribution that made the project and content get that far. Thank you. This is it. Thanks for watching this presentation from TU Berlin entitled Accuracy Analysis and Improvement Method for Continuous Web-Based Precision Assembly. Thank you very much.